Today we talk about floating point arithmetic. We talk about numbers. So we have two integers, 123 and 29. We divide them, and what do we get? We get a really long number. It's an infinite number. Or we take pi, a symbol. Everybody knows what pi is. If you want to look at the digits of pi, you call Mathematica, you ask for the first 40 digits, and that's what you get. So in general, numbers in the mathematical world have an infinite number of digits. So infinite. All right. Here's a contrast. In general, our computers, it's very likely that they have a finite amount of memory. By very likely, I mean it's a joke. It's obvious that we cannot use but a limited amount of memory, limited amount of hard disk, limited amount of resources. So there is a conflict here. We have infinite objects to be stored into finite resources. So here is the contrast, and how do we solve the contrast? By approximating the numbers. So, how many digits should I use to approximate a number? Well, I have to decide. That's what we do in computers. We decide how many digits I can use, and I truncate or I round, and I discard everything else. For instance, if I choose 4, if I say that I have enough resources to store 4 digits, my pi becomes 3.141, and everything else is gone. We will see in a few slides that normally in our computers we use either 8 or 16 digits. And these 8 or 16 correspond to single and double precision. We will talk about double precision all the time, floating point numbers, doubles all the time. Okay, do we have alternatives? Yes, there are alternatives. We can even go to extended precision, which will be 32 digits. It's called quad precision. It's not very used in practice because the processors are not able to execute operations on quads directly. So they have to simulate the quad arithmetic, and that's why it's so slow. Processors are able to execute arithmetic on single and double precision numbers directly, and that's why they're very fast on that. There are libraries that allow you to use any precision you want. So you want the numbers with 50 digits, that's perfectly fine. These libraries will be slow as hell, but they allow you to carry on as many digits as you want. And we will work with one, Mathematica. Alternatively, well, if pi is a symbol, why not to just treat it as a symbol? What I mean by that? Well, maybe I can have a language that remembers the concept of pi as a symbol. When then I say pi square, it doesn't have to go and compute 3.14 blah blah squared. It simply remembers, okay, I have a pi and I want to take it as a square, and so on. And at that point we forget about the numerical aspect, the numerical concept of pi. We simply treat pi as a symbol, and we just carry on with this symbol throughout the computation. All right. So we have seen already how numbers have to be approximated, which means that in our mathematical world we have accurate, exact numbers. In the computers we have approximate numbers. Okay, let's see if our arithmetic at least is exact. So when I work with numbers in mathematical terms, I never make a mistake. If you make a mistake, you get a bad grade, and you learn how to do additions and subtractions, multiplications. Is it the same on in computers? Unfortunately not. So not only the numbers are not accurate, are not exact, also the arithmetic is not exact. Over here I'm adding two 4-digit numbers. I said that 4-digit numbers are admissible. That's what my computer understands, so that's fine. That addition is perfectly defined. Unfortunately, the result uses 7 digits, and my computer only understands 4 digits. So what do we have to do? We have to eliminate 3 out of these 7 digits. And we can do this in different ways. We can truncate, saying, okay, I discard anything that comes after the 4th digit, so 6, 7, 8 just drops. Or I can round, so I can sort of approximate this number. I see that it's 123.9, but it's not really 9, it's 9.6. So 6 is closer to, 9.6 is closer to 100 than it is to 90. So I can actually round up. This means that when I do my computation, I carry one more digit, and depending on this digit, I round my 4 digits. And this is what actually happens. And as a matter of fact, you can set your compiler, your language, to react in different ways. You can round, there are different ways of rounding. I'm not going to cover them, but you can set what type of arithmetic you want to use. Okay, this is probably the most important concept, at least in this first part of the slides. Mathematically, our numbers and our operations have a whole lot of properties that we would like to be satisfied on a computer as well. Associativity is one of them. What does it mean? I have A, B, and C. I add them up. Mathematically, it doesn't matter if I add A and B first and then C, or B and C first and then A. So now let's look at the math on a computer, and let's see if associativity still holds. Remember that now we have inexact arithmetic. So I add these numbers. My result has 7 digits, so I have to drop. I have to go down to 4 digits. Okay, now I look at the other ordering. I add these 2 numbers first. I go back to 7 digits, then I round, and the 2 expressions yield different results. So associativity on computers, no. Even the most basic operations like additions cannot be performed exactly. They introduce slightly little errors. Okay, now let's abstract a little bit. As I said, when we write a program, what we're really doing is we're trying to replicate a function. We have a mathematical function in mind, and we are writing a program that hopefully is computing this function. Okay, let's say that our function is that x squared plus sine of 2x. And I want to evaluate, I want to find out the value of f in x when x is pi over 123. Okay, over here you should realize that this computation will be pretty hard on a computer. We will be making all sorts of mistakes. So let's see which kind of mistakes. Pi cannot be represented in finite with a finite number of digits, so it will have to be approximated. We have a division, pi over 123. The division will introduce errors. Okay, that's just where I want to evaluate my function. I will not be able to evaluate my function exactly in x, because the point x, I cannot represent it exactly. So I will be able to evaluate my function somewhere near x, but not exactly in x. Will I be able to actually evaluate f No, unfortunately not. Why not? In f I have this sine. The sine function, it's not that I take two numbers and I add them together. Computer can do that, but a sine function, you actually have to go for a Taylor expansion of the sine, and then you have to add up a bunch of terms. So you will have to truncate this Taylor expansion. The more terms you use, the more accurate it will be, but you can certainly not sum up an infinite number of terms, so there's going to be an algorithmic error. In practice, the sine and cosine functions, exponential functions, are actually stored in hardware. There are some lookup tables, and that's how sine and cosine is computed. Not by actual computation, but by going into the hardware and reading in some tables. Okay, so we have to, the sine has to be approximated. This has nothing to do with the actual arithmetic. It's just the concept of sine. When you transport it into a computer, it becomes an approximation of sine. It's not the function sine anymore, it's the approximation of it. And then you have to, not only you have an approximation of sine, now you have to evaluate it in a point that is approximated. In exact arithmetic, this is no big deal. You can do it by hand. It's, in exact arithmetic, x moves to x hat, f moves to f hat, and so you end up evaluating fx at x hat instead of f of x. And in doing this, you will make mistakes because of the arithmetic. So this will be even further away from f of x. So you always have to keep in mind that the operations, there is a mathematical definition and there is a computer counterpart. And the two things are not the same. Next Thursday, I will not be here, but a student of mine will give a presentation. He will talk about two or more known disasters. For instance, this is when the US bases didn't catch a Scud. The Scud was in air and it had been detected, but it was not shot down. And the reason for this was a mistake due to cancellation. Cancellation is when you add very big numbers with very small numbers together, and I'll give you an example later. Or when you add when you add a big number and a big number but negative together, this basically eliminates leading numbers and results in noise. I will show you an example later on. Maybe a more spectacular disaster is when the spaceship Ariane 5 took off and exploded about 40 seconds after takeoff. This was because two softwares were involved into the control of this spaceship. One piece of software was taken by spaceship Ariane 4 that was in fixed arithmetic. Ariane 4 was a much less powerful spaceship than Ariane 5. Now they use the same software on Ariane 5. Ariane 5 had a much more powerful engine that caused an overflow, and then the second software, the one on board, that was supposed to take over and control the flight, is just inherited an overflow from the first software, and it caused the crash. So my student will present this next week. For now, let's get into the details. So this is really the nitty-gritty of what happens inside the computer, how numbers are are actually stored. So this is the general definition. Floating point number is represented like that. Y is a floating point number. We have a sign, plus or minus. Then we have t digits from d1 to dt. Then we have a b, base, and e, an exponent. Let's go one by one. B is a base, radix. Which base do you guys think is used in our computers? Yeah?
2.
Any other take? 10. Who said 10? So, no, it's not 10, but there were computers in base 10, and I'll tell you about that in a little bit. 10 is a really good base for some reasons. I'll tell you later. Okay, T is called the precision. It's the number of digits that we can use, what I mentioned before, that we can use to store a number. It's these digits altogether are also called mantissa. So the sequence D1 to DT, they are the mantissa. Each digit goes from 0 to the base minus 1, beta minus 1. Just think in terms of base 10. Each digit, of course, goes from 0 to 9. If we are in base 2, we go either 0 or 1. There is an exception. D1, well, I'll tell you in a minute, but there is an exception. D1 is actually normalized, and we force it to be 1. I'll tell you in a bit. Okay, the exponent, that's what regulates the expressivity of my floating point set. This determines how many floating point numbers are in my system. And then here you go, what I was just saying, normalization. The first digit, I always assume that is a 1. That means that that digit is in fact used to store the sign. Otherwise, I would need another value or variable, something, to understand whether the number is positive or negative. Well, in reality, the first digit is a sign. Okay. These are the single and double precision arithmetic that we always hear about. Let's do a little bit of calculations. The base is 2, as you suggested. That was correct. T is 24. What is T? Is the number of digits. 24 digits. And the exponent can vary. The range for the exponent is from minus 126 to plus 127. These are integer numbers. Okay? How many digits do I need for the exponent? Yeah?
8.
Why?
Because if you think about it, there are 256 different values, and that's 2 to the 8.
So let's see, 126 plus 127.
Plus 1 because of the 0.
Okay, that's not 256. 127 times 2, it's 254. So it's still not 256. But it's true, since it's 254, I need to go to the higher power of 2, which is 258. So and I need 8 bits plus 24 means 32 bits. So when we talk about single precision numbers, we talk about numbers that fit 32-bit registers. Let's look at double precision. Same trick, same story. We have 53 digits, okay? Keep in mind that these are binary digits. These are not base 10 digits, okay? So I'll do the conversion in a minute, but 53 digit, how much is 1024? 10, very good. So this is probably 11, right? 2 to the 11th. But 2 to the 11 is actually a little bit more than that. It's 1024 times 2, so 2048. And this is 2046. So we are losing, for some reason, we're losing 2 values. Anyway, we said that we have 11 plus 53, we get to the magic number, 64. So when we talk about double precision numbers, we talk about numbers that fit in a register, in a 64-bit register. Before I explain where these extra numbers are gone, these extra exponents are, let's look into other arithmetics. And here it is. We do have a base 10. In the HP calculators, we had the base 10 arithmetic. The best one is in this Russian computer. It's the only computer that has a base different than a power of 2. And it was fantastic for a number of reasons, and it was a horror story for many other reasons. And in fact, it never caught up. So that's the only example. Okay, as I said, the base 10 has a very important value. Can anyone guess why base 10 is so important? For what reason base 10 is so important? Yeah?
Because humans tend to think about things like 0.3 in base 10, and it's very hard to write that as base 2 without rounding.
Yes, but we don't care about humans. We're talking about computers.
Maybe you should.
Yeah?
Well, a lot of numbers have an infinite representation in binary, and they do have a finite representation in decimal numbers. So they are.
This is true. Basically, you guys are saying the same thing, but I'm asking, there is one particular application where these digits that seem to get lost are very important. And it is?
Finance.
Yes, it's banking. Base 10 is so crucial because of banking. They do not want to lose even the last tiny bit of accuracy. So they do not use double precision. Every banking software actually simulates base 10. There are stories, I hope my student will present these stories next week. There are stories on how the trade exchange actually went almost bankrupt because of a truncation error. They were basically truncated every transaction, and the global index was going down, 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 to the point that there was a crisis. They just recalculated every transaction, rounding, and the index just jumped up to. So it's a beautiful story. Okay, this is the extended precision. And now you see, if you do the math, you go up to 128 bits. Okay, here is an exercise for you guys. So I want some volunteer. I want to plot all the floating point numbers in this particular arithmetic. So this is when I stop and somebody comes to the board and does this for me. Do I have to use the Matlab volunteer generator, or somebody actually volunteers? Matlab volunteer generator is nothing else but a random generator, and somebody comes. Come on, guys, don't be scared. I'll help you. Somebody? Really? Okay. So, see, I use the random, the volunteer generator. How many is it here? 5, 10, 15, 20, 25, 30, 35 today. So, mm, 30. So this first 5, 35, yeah. Come over. Okay, what do we have to do? We have the x. These are our numbers. Let's place the 0 here. So now you have t equals 3, so you have 3 slots. Plus or minus, but we only care about plus, okay? Then the first one, we said that it's normalized, so it's always a 1. So you only have 2 slots. Then you have times 2 to the e, and e varies -1 less than e less than 3. Okay?
Okay.
Oh, you want more?
Negative points. Non-negative points. Well, actually, I quite have problems with the mapping from this Darstellung.
Base?
From this presentation to
Mhm.
Our normal decimal.
Let's do it together. So, we have 3 digits, d1, d2, d3. The first digit has to be a 1, so there is nothing to do. The second and the third digit, we are in base 2, so they can only be either 0 or 1.
Yes.
Okay,
So,
so
for
let's,
example.
yeah, for example. Okay,
And well, just this is so
yeah,
principle, so it's I just take 1, 0, 0.
okay, times 2 to the
2,
power of,
2, 1, 2, 3. So let's take 2.
okay. So, this is a point.
Yes. So.
So if this were a 0, this will become a 1, which means you're not multiplying anything.
Okay. So this means this is a half.
Very good.
I see. So, for instance, this. So this is a half. This is
The fourth, yeah.
So, it
Three.
was
3/4.
3/4.
Yeah.
And I have to multiply them by 2.
Mm-hmm.
It's
Si-
3 half. 1/5.
Very good. Okay.
Okay.
Now
I see.
let's be systematic. Okay. So let's start. Which one is the smallest number? Write it here so everybody can see.
Intuitively, the smallest number I would guess it's this. So this is.
Wait. Comments? Very good.
Huh?
The first one must be a 1.
Okay.
Okay. Other objections?
1, 0, 0, 0.
Yeah. Why not?
Then
Because you said e is bigger than -1, not equal to -1.
Sorry, you're right. Very good. Okay, so does anybody object? Is this the smallest number? Yes, you are.
It's the smallest positive number.
Yes, it's the smallest positive number. This is true. That's why I circled the plus. Let's stay on the plus side. Okay, let's compute that. Yeah?
I'm not really sure why is 0.1 times 1 equal to 1/2?
Say it again.
I don't understand why this math doesn't make sense.
So this is 1,
Yeah.
and this is a half, because this is 2 power to minus 1, and this equals a half, and so, I'm sorry. So it's a half times 1.
I don't know, because 0.1 times 1 is 0.1.
It's binary. It's not 0.1, it's a period and the digit 1 in base 2. It's not in base 10. Yeah. This is the value of each, the importance of each digit. This is on the left of the period. We are into the integers, so 0, 1. Here we are into divided by 2, divided by 4, divided by 8. So let's look at the smallest possible number.
So this is a half, this is a half, this makes a quarter.
All right, so let's go. Here we put 1, and we decided that a quarter is our smallest number. What's next? The next number up? No, someone else. Next number up? Yeah?
It's 0.1011.
Yeah?
2 to the power minus 1.
Yes.
What is it?
It's half plus 1/8. No, no, it's not over 4.
This is
It's
4
it's a
eighths,
plus.
this is 5 8,
Oh, that's right. Yes.
and
Yeah.
my mistake,
Okay.
16.
16. Can anyone compute that? So actually, let's do 1 second. Let's do something smart. We are 1/8 away. This is 1/8 away from that, and it's what is it?
13125.
Yes. But keep in mind, it's 1/8. It's not. This is 25. This is. Oh, it's not one. It's 1/16. Yes. It's 1/6. No, it must be 1/8 more than that. How much is 1/8? 1125. Yo, so it's fine. Is that fine? No.
No, it has to be 1/16th away because of the multiplication, so it's 1/16th away.
No, I disagree. No, maybe I agree. Okay. All right. Fine. Next. What's the? Yes, I agree. What's the next number up?
So intuitively,
Yeah. Which is? You did something close to that already. You just have to change the exponent.
okay.
It's 3/4. So it's 3/8.
yes.
And it is? 375. Okay, what is the distance between these two numbers? Which is the same as the distance between these two numbers? You agree? So it's once again the same. 16. Next one up.
Shall I continue?
Sure.
Okay.
Something happens pretty soon.
7/16. Thank you.
Okay, I'm just gonna write it. Same distance, and this is 7/16. Okay, what happens next? Nope. That's exactly what happens next. It's a surprise. Exactly. Now we change the exponent. So we don't go in steps of 1/16 anymore. We go in steps of 1/8.
Yeah, but the next is still 8.
8/16 is good.
And that the
Yeah, okay.
After that, wrong.
That's right. Yes. Right now we're still good. What is it? 1/2. So, hey, look at that. I actually am in a half. Genius. All right, next. Yes, that was the last step of 1/16. Now we can actually do it almost by heart. Almost. How much is 5/8? Well, it should be.
And 8/6.
Okay. So I have to divide it. It's here. 5, 6 to 5. Next. Very good. Yes, you can do it. So, sorry, you can do it automatically. That's 3/4. Then you divide the distance between 3/4 and 1. It's 7/8, which is here. Then you jump to 1. What's going to happen next? The pattern should be clear already. Now you have to double the size. We go up. So we don't jump into halves anymore. We just go like this. So let's just try the next one. 1, 0, 0 times 2. So that's a 1, okay. Then which is here, 1.25, and then we know 1.5, 1.75, and 2, and so on. What is the largest number we get? Plus 1. And so we continue, do 2. Well, that's pretty, somewhere around here. There is a 7. Okay, thank you. See, it wasn't so bad. Okay, what did we get? The floating point numbers are non-equidistant. So you see that there are many, many more floating point numbers close to 0 than far away from 0. Actually, there is this. There is some problem. There are right close to 0. There is a really big gap. Can anyone tell me why there is that huge gap there? Yeah.
Because we have the first digit fixed.
That's exactly right. This first digit causes a really large gap here. If you think about it, that gap is actually not so large because it's going to be a very, very small number multiplied by a small exponent. But it's very large when compared to how many floating point numbers are right next to it. So in practice, and by the way, every number that falls in here causes an overflow. Yeah, right. Underflow. Underflow. In reality, the processors are not so stupid, and they implement what is called gradual underflow, which means that they denormalize, they try to salvage the computation, and so the causes of underflow are not as severe as what I just depict here. Yes?
Why is the first digit fixed anyway?
For speed reasons. makes things much faster, I believe. But I can give you pointers to papers if you want to explore it. Okay, if you get numbers beyond the largest floating point number representable, then you go into overflow. So underflow is down there, overflow is up here. And then everything is symmetric for negative numbers. Underflow and overflow there. So let's continue. We didn't find the zero, did we? In our representation, we were not able to find zero. And this has nothing to do with the plus or minus. Anything we did for the plus would be mirrored, and we would get all the negative numbers. We didn't encounter a zero. Can you guys tell me why or how to represent zero?
As long as we have guaranteed 1 after the dot, and we have a non-zero basis, we can never show a zero.
But for sure you have seen a zero in your computers, right?
So what we have to do is we have to, which magically fix the underflow problem a bit, we have to allow certain denormalized numbers. So we have to not normalize everything if we want to do that.
That's not what happens. So we have to, the zero is dealt with in a different way. Anybody can guess? Yeah?
Some unused representations. You can just
Very good. Didn't we say that we lost some space, some representations here with all of these exponents? They do not add up to 256. They do not add up to 2048. Why not? Because there are some special representations used for zeros. In fact, we have representations for positive zeros and negative zeros. Like when you have a limit, and you approach zero from the left or from the right, we have different representations for negative and positive zeros. We have representations for underflow. We have representations for overflow. None. Do you know what none is? Not a number. It's actually a quantity understood by the processor. Depending, you can store this quantity, you can deal with it. You can store infinity, all with these special representations of the exponents. So let's look at the bisection. What is bisection? Is a way of computing the zeros of a function, polynomial or whatever other function. Let's look what it does. We have a function, could be the x squared plus sine of 2x, something like that. It doesn't matter, any function. And what I want to do, I would like to find the f of x, the axis, such that f of x equals 0. So, a very common algorithm is the following. It's based on this. This is the idea. Magically, somebody tells me that in a point A, my f of A is negative. And always magically, somebody else tells me that in B, why do I put it on top? I don't know. Somebody tells me that in B, my f of B is greater than 0. All right. Then what do? We study the continuity of the function. Oh, look at that. Sine is continuous, product, plus. Okay, everything is continuous. Great. there must be a point, at least one point, between A and B where my function intersects the axis. I don't know the function, but for continuity, it must cross the axis at least once. It could cross it more than once, of course. Okay, at that point, if I am in this condition, in this situation, what would you guys do? Precisely. That's a little bit of a cheat because you've seen my last course. Okay, so I would divide the interval in half, so I would go in A plus B over 2, and I would ask myself, what is f in that point? Greater than 0, less than 0. Or if I got really lucky, maybe I got the 0. Okay, if I got the 0, then I'm done. Let's say that f in the middle is still greater than 0. Then what should I do? Yes, then you're saying go left. And now we're going to write it out. If it's less than 0, I go right. Okay. Anybody confused so far? No. Okay, let's write a recursive function that actually computes this. So we have bisection. Bisection takes a function, takes a left, takes a left and the right interval. And the right value. What we know is that, let's say that we know that f of L is, so understanding what is the semantics of that, the meaning of that. We know that f of L smaller than 0 and f of right is greater than 0. Then we would have a different function where f of L is greater than 0 and f of right is smaller than 0. But okay, let's be stupid. All right, so we know that. What do we do inside our function? We open the environment and we say if. Suggestions? Sorry, say it again? So if of L plus R divided by 2, okay, what? Greater than.
Sorry. What am I saying? F of L plus R by 2 times f of L is greater than 0. Then something.
Times f of L greater than 0. Okay.
No, less than 0.
Okay. You like less than 0. So f of L, we know that is less than 0. We are evaluating the function in the midpoint. We multiply these things together. If it's less than 0, it means that one is above, the other is below. Okay, then what do we do?
Then we calculate f of, bisection of L and L plus R.
So L.
And L plus R.
Yes.
Why do we need the times f of R?
It's just a trick. It's not the first thing I would think of, but it's perfectly fine. It's basically saying that if one is less than 0 and the other is greater than 0, their products is less than 0. You could say, if this thing is greater than 0, then do that. Do you like? Yeah, it's absolutely the same.
Then this is not the stupid case, right? And this
Yeah, I know. Let's not get into, I know. Else. So, what do we do else? Else?
Else if it's less than 0, it will become as the following.
So if f of blah 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 is less than 0, then okay. Do we have something else to do? Sorry? We can do else if, else if, then else. It doesn't matter, okay? But what should we test, yeah? What do we do then? We say we print success and maybe we return L plus right divided by 2. Okay. Sorry? So that was my question for you guys. Who thinks that this is a really stupid algorithm? Oh, somebody. Okay, who is against, what is wrong with this algorithm?
Well, for one, we could end up in a tricky situation that we need a lot of time to almost get close to 0.
Mm-hmm.
So maybe it would be more appropriate to check whether we're, say, within, what was it, 2 to the negative 53 or 0.
Mm-hmm.
You said we have several representations for 0. If we are coming from the left side or from the right side, so we don't know what representation of 0 the 0 which we are comparing to.
Okay, I like this too, yeah?
We could get stuck in an endless loop because you cannot precisely hit the 0 center.
Precisely. Come on, guys. You cannot compare against the 0. You just cannot. This is a really, really stupid thing. I mean, it could possibly happen if you have ever done anything in probability. It's an event of probability 0. It could happen, but it will never happen. So you cannot compare against the real number. We're not talking about integer numbers. If you work with integers, it's a different story. When you work with the real numbers, you cannot compare against one specific number. I just showed you before that two numbers cannot get any closer than 2 to the minus 50 power of 53. So here we're trying to compare against one specific number. Very, very bad. Okay? So let's scratch this algorithm. What you were suggesting is correct. So let's look at something else. We don't like this. Okay, we enter our function. Maybe we should do the following. We have a suggestion, yes?
We just observe the left and the right until there is no farther, until they just stay like that. I mean, they cannot get any closer.
So, okay, let me give a suggestion. How about we start off and we say, if left equals double equal, if L equals right, then we print victory. And we just give either left or right, it doesn't matter. Then we do else And we do the same story. Else if greater than 0, bx blah blah blah, or else bx blah blah blah. Thumbs up? No? Thumbs down? Down. But what are you? Yeah?
Shouldn't you check not for equality but for the distance between?
Thank you, thank you.
Below some-
Super bad. I'm comparing two real numbers. Can they ever be the same? It's exactly the same as comparing against 0. No. No, 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 no. Really bad idea. This is as bad as the one before. So, finally, looks like we got down to something meaningful. How about if the distance between left and right is less than some delta, then we print victory. Okay. Then we say if ba 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 and then else ba ba ba. Okay, fine. How many of you are happy with this?
Say if you exchange the 0 for delta.
If I do what? So not everybody is happy yet. Who is happy? I see somebody happy down there. Yes?
I don't know yet.
Nobody is? Well, if you're not happy, maybe you are unhappy. Yes?
Can compare the function value if it's close to 0. If your delta is
Okay.
Bigger than the function value, you have enough.
Fine, that's fine. I consider the two things equivalent. So, yeah?
The addition might cause problems.
This one. You are actually absolutely right. There are better ways of computing that thing. Instead of adding two things together and then going back, you can start from one and go halfway towards the other. So that is correct. But I'm looking at this statement for now. What he's saying is absolutely correct. There are better ways of computing this number. The function is a different story. What about here? I'm asking, this would be the base case, the termination, right? We want the recursion at some point to stop, and I'm trying to define when to stop. Yes?
And the delta is still a problem. You must know what value it should be, or
I like this. Yes?
The delta is dependent on the scale of elements. If the
Is it?
yes, because if you have large LFR, their difference is on a different scale than if they were smaller. So the smallest delta for big LMRs is larger.
Okay.
Depends on the scale.
Yes.
I would say something similar like if L plus L divided by 2 is L or R again, then it should be.
So, we are, 1 second. We are comparing two numbers. And we know that two numbers cannot agree for more than 16 digits. This is very true. But he's saying, hey, but these 16 digits are multiplied by a scale, by an exponent. So here we are comparing in absolute value. Maybe we could or should divide by something like the maximum of L and R. Yeah? Then it would be a relative criterion. Anyway, everything depends on how we define delta. This is the crucial point. And now, finally somebody got it. Okay. here we go. So I don't know how you're going to do it in the video, but the right answer for this is yes 2 to the, oops, I deleted it. Is yes 16 digits, but when we talk about an absolute number, you have to scale times the exponent. So that's probably why you were so confused. So in terms of digits, two numbers cannot agree for more than 16 digits. When we go into mathematical terms, the actual distance, the value, that depends on the exponent. So we have 16 digits, but we can shift, and we can shift by a lot, because we go from minus 1,000 to plus, from 2 to the minus 1,000 to 2 to the power of 1,000. So now I hope you guys really got it. Two numbers, they can never agree for more than 16 digits. When you look at the actual distance in mathematical value, you have to look at it also the exponent. Okay, yes?
You also have to be careful with using something like the maximum, because the maximum could still be negative, in which case we would immediately return and say, great, we're done.
Yeah. So it's a maximum of the absolute values. That's correct. I'm skipping a lot of details. Anyway, let's just conclude with bisection. When you're comparing objects that are going towards zero, or they're going towards one another, you always have to switch to tolerances, to bounds. You can never ask whether a quantity equals another. That's something you cannot do on computers. You always have to ask yourself if this quantity is in a neighborhood of another. So some either absolute or relative distance. Sometimes absolute is good, relative is normally better, and then you have to put a tolerance. How small can this tolerance be? Let's do this for now. How small can a tolerance be?
Has to be a little bit greater than the machine precision. So
What is a machine precision?
to the power of minus 16.
Yes. If you're very ambitious, you set it close to 10 to the minus 16, to the machine, close to the machine precision. But you don't know if the computation is so accurate. The more computation you perform, the more error you generate. So maybe you want to be a little bit generous and say 10 to the minus 15, but you cannot judge how much error will be generated by the algorithm. This to study the round of error, so how computers generate and accumulate errors, that's what we will look into just briefly. But to look at that, there is a whole branch of numerical analysis. So there is all this area of stability analysis, error analysis. Part of the story is that your computation should be as accurate as possible. But part of the story is that maybe the problem that you're looking at is ill-conditioned. So let me just give you the intuition behind the ill-conditionedness, and then we move on with another example.
So when you say they can differ around 16 places, you mean decimal places?
Yes, decimal places. Yeah, in that case, I talk about decimal digits, yes. Or 53 binary digits, if you are a binary person.
Well, you're talking about binary all the time.
All right, so We have two lines in space. We want to compute the intersection. What do we do? Can anybody see a linear system arriving? Yes, I see some faces nodding. I like that. A, B, D, E, X, Y equal C, G. Linear system. Very, very good. You solve the linear system, you find X equals, Y equals, and you find this guy here. Well, there are some problems in working with computers. Our input data, A, B, D, E, C, G, will be a little bit far away. I showed you already that numbers have to be truncated, rounded, approximated. We will work, instead of working with those numbers, we will have A bar, B bar, D bar, E bar. X, Y equal C, G. Bars. So the problem has changed a little bit. Then we will have to compute the solution. So X and Y will be the result of some computation. We will have an algorithm that takes a matrix and does some operations. What we're trying to solve is AX equals B. What do you guys suggest we do? This is, who knows me, this is when I might kill somebody, so this is the right time to give me the right answer. What do you suggest we do? We want to compute, unfortunately this X is not the same X. This is, and this B is not the same B, so let me rewrite it. Capital A times a variable. Variable, give me a variable. Delta equals, see. Yeah. Yeah. This is my followers. So how about somebody that doesn't know me? What do you suggest with... No, you don't say that. Do you have other suggestions?
Well, we first solve for X and then we solve for Y.
Absolutely, but we only have this. I'm abstracting, I have a matrix, an unknown and a known right-hand side, and I'm trying to compute delta. What do you suggest we do? Ha! He said it! He finally said it. Okay, this is the first and last time in the semester that you will say inversion. Okay? Don't ever say inversion. It's the same as Microsoft. It's the same thing. Don't talk about Windows, don't talk about inversion. So you never do this. Never ever compute this. As my followers rightly suggested, we compute an LU factorization or some other factorization depending on the properties of A. At that point we have LU delta equals C, and we have to solve this monster here. So we solve it in two steps. First we call this, we just assign a different name. Now I need a different name, W. And we solve LW equals C. W is an unknown. And then we do U delta equals W. That's how we solve a linear system. Okay, so we started from, we wanted to compute the intersection of two lines, and we went all the way to an LU decomposition and two triangular systems. If you don't know what these L and U matrices are, it doesn't matter, I will just cover them much more into details. I just wanted to make a point. Don't ever do this, because this creates lots of round-off error. Actually, to be fair, it's not the computation of the inverse that creates the round-off error, it's the multiplication of the two, and that takes you way off. Okay, questions about this? No. Since we're here, I want to make another point. Now we are in this situation. Our two lines are very close to one another. They are not parallel, but almost parallel. Do you guys see what happens when I perturb the matrix a little bit? And by matrix, I mean when I perturb the input data a little bit. If I move this, okay, yes, yeah, you?
So there's a large area where the distance of the two lines is within the machine, smaller than the machine precision?
I don't see machine precision yet, but what I see is that there is a really large range of points that are close to one another. When I twist the line just a little bit, this point moves a lot. Over here, if I move the lines just a little bit, the point is still over here in the neighborhood. But when the lines are almost parallel and you slant them, squeeze them a little bit, this point moves by a lot. What is the difference between these two problems? Sorry, you have the question?
I had another thing that could go wrong. If you're very unlucky, your input data could become the same, and then you couldn't solve the linear equation system at all.
Yeah, the answer is precisely the same. What distinguishes this situation from that situation? Yeah? Yes. So the answer is that the problem itself is ill-conditioned. So this has nothing to do with how we solve the problem. It's just that we're trying to solve an ill-conditioned problem. What does ill-conditioned mean? It means that the problem itself is very susceptible under little changes. So if you perturb the input data by a little bit, the solution changes by a lot. And this, again, has nothing to do with computers. It's just that mathematically, if you perturb these lines a little bit, the intersection point moves by a lot. So the problem itself is ill-conditioned. On top of that, you add the fact that we use approximated numbers, and we use inexact arithmetic. So if a problem is ill-conditioned, we are in bad shape. Okay? And it's not necessarily because our algorithm sucks. It's not because we don't have enough accuracy. It's because the problem itself is ill-conditioned. I have a lot more to present, but not so much time, so I just want to amuse you for the last 5 minutes. Let's go to the next example. Let's say that I have two algorithms for computing pi. Mathematically, I know that this infinite sum adds up to pi squared divided by 6. So you just have to add an infinite amount of numbers, and then you take the square root, you multiply it by 6, and you get pi. There is a little problem, the infinite sum. So what I'm showing here is that, of course, I have to truncate this sum at some point. Let's say that I take 10,000 entries, elements, and I add them in two different ways. Over here, I start from 1 to the 10,000s, and over here, I start from the 10,000s, and I add to towards the first one. Do you see any difference? Yeah?
In the right one, we first add up all the small numbers, because the I squared is very big for big I, and therefore the 1 over I squared is very small. And by doing that, we sort of can gather our digits and don't lose them to truncation early in the computation.
So his suggestion is the right one is more accurate than the left one. Does everybody agree? You disagree a lot. Okay, so since I want to have fun for the last 5 minutes, I wrote something. What did I call it? I don't remember what I called it. So this is Matlab, but for today it doesn't matter because we're not really doing any Matlab. We're just looking at what I wrote. Summation. Okay. So this is a super little program that does exactly what I showed before. And it starts from 1, it goes all the way up to 5,000. And I'm using single precision numbers, otherwise I would not be able to show you anything. With double precision, everything is fine, so I use single precision. Okay. And I should put this. This is what I have computed. Just to give you an idea, my pi equals pi square over 6. So abs t minus my pi. Okay, I have computed pi square over 6 with an accuracy of 10 to the minus 4. And I used 5,000 entries. So now I will use 15,000, and actually and then I do this. Okay, I have used the same 5,000. That was not very smart. So let's use 20,000. And my accuracy is exactly the same, no improvement. That kind of sucks. Okay, so let's look at the other way around. Now we go from 5,000 down to 1. Okay, nothing changed. The accuracy is still the same. But notice that now I'm going the reverse order, okay? So, calm down. Now let's go to 20,000. Oh, something happened. Now I am a little bit more accurate. Let's go 100,000. And so 20,000 was 5. Here is here I went 5 times as many entries, and the accuracy is actually 5 times better. So let's see if there is some rule. Now I'm going to go 500,000. Takes a little bit longer, but I am still improving. With the other method, once I passed 4,000, as a matter of fact, there is no improvement anymore. Here I am at 500,000 entries, and my accuracy is still improving. And the why is because in one case I start adding the big numbers first. The big numbers occupy all the 16, actually I'm working in single precision, so they occupy all the 8 digits, the 8 significant digits, and then I add the smaller numbers later, but all these smaller numbers have no influence in the large ones. When I start from the small one, I start from very little numbers, and I keep adding very little numbers, so they little by little create a larger and larger quantity, and as I traverse, I keep adding always a little bit larger, always a little bit larger numbers, and this process, this effect actually propagates, and in the end I'm able to get closer and closer to the right solution. I don't have time to give you more examples, so I'll see you on Tuesday.